morning again. So, in my previous talk lecture, I told you about this system. Now, it is little bit problematic, do it this way. Let me bring it here. And this was a fluorophore, means anthracene. I am writing it as F. F stands for fluorophore. So, I told you that this is the first report anywhere stating that transition metal indeed causes fluorescence enhancement. Earlier it was understood that transition metal quenches fluorescence. So, we cannot have systems where transition metal will enhance fluorescence. Okay. So, quenching of fluorescence was taken as presence or absence of transition metals, but it is always important to have, for practical purposes, always important to have fluorescence enhancement rather than fluorescence quenching. So, this is the first example anywhere in the world to show that transition metal indeed causes enhancement of fluorescence, and this was done here, right here at IIT Kanpur, and reported in 1995. We talked about that, and since it was a very first time, so we did lot of physical studies also. Okay. So, not only this spectroscopic studies, okay, we did lot of other studies as well with this fluorescence, and one of them or two of them I will discuss today. One is called exciplex. These things are very important, and we will refer to this exciplex later, sometimes later with other systems. What is exciplex? Exciplex stands for excited state complex. Excited state complex is called exciplex. Okay. So, when fluorophore is excited, when I excite my anthracene, then that anthracene, there is no metal here. There is no metal here. That means the lone pairs are still available. Lone pairs are available, and when I excite my fluorophore, that excited fluorophore interacts with this lone pair. Okay. It interacts with this lone pair, forming what is known as exciplex. That means an exciplex comes, it comes like this. So, when there is no metal, all right, there is no metal present. So, when I excite my fluorophore, my emission, that is called monomer emission. The emission that I am talking about since yesterday, that is called monomer emission. Monomer emission is quenched. Why? Because of PET. So, it is quenched. However, it gives a broad band. Okay. So, you increase the concentration, increase the concentration, this band intensity also increases. And this is around, this is a broad band. Usually fluorescence with anthracene are sharp bands. I will show you in a minute. So, this is around 520. Okay. So, this is around 520 nanometer. I get a broad band signal. And what is the origin of this? The origin is that excited state fluorophore interacts with this lone pair, nitrogen lone pair, all right, which necessarily means if I have a metal now, if I have a metal, then these lone pairs will be engaged to metal, lone pair will not be available anymore, because it will bind the metal ion, that is the property. Then what I will get? Then my exciplex will vanish, because lone pair is not available. So, no exciplex. When metal is there, no exciplex. So, it will not work. So, what will happen? My spectra will look like look like this, something like this. Okay, this is the 0 band and these are vibrational fine structures. This is due to anthracene. Anthracene monomer emission, anthracene. So, this spectra, entire spectra we call, these are anthracene monomer emission and these are vibrational fine structures, these two on the either side. And my exciplex is gone. So, exciplex, appearance of exciplex is also very important in certain situations. I will talk about that later in some other systems. Okay. So, we did lots of photophysical studies, and so you should know when you are doing fluorescence studies, you should know existence of exciplex. Another thing is very important, that is called excimar, that is also very important. Excimar. Excimar is the is the shorthand of excited state dimer. This is excited state complex and this is excited state dimer. So, what can happen? Suppose in a situation like this, if we have more than one, or say, let me draw a cartoon and show you. Suppose I have, this is exciplex and I am writing now excimar. Suppose okay, so here is a anthracene. I am not writing fluorophore, anthracene. Okay. And this let me write F. F stands for anthracene. Now, another molecule can come. Another molecule can come. Another molecule can come. Let me bring it. Just for the argument's sake. Okay. So, I put this molecule close to each other. Therefore, there is one anthracene molecule, anthracene moiety from the left one and this one from right side another comes. So, it can make a stack. So, when it is stacked, this will give us what is known as XIMR, excited state dimer. Okay. So, this will give, and fortunately or unfortunately for anthracene, this XIMR also comes here in the same region, a broad peak. So, how do I know it is XIplex or XIMR? This is XIMR. How do I know? If I know if I increase the concentration of this, okay, we take concentration 10 to the power minus 6 molar. So, that is very dilute. So, we know that two molecules coming like this is very remote, it cannot come. So, it is not XIMR, it is probably XIplex. To make sure, what I can do, I can increase the concentration of this fluorescent signaling system from minus 6 molar to I can say I can put to minus 3 molar. Then there are more molecules of this and they are supposed to come and then stack. So, XIMR. So, in another words, if I increase the concentration of the fluorescent signaling system, then I will expect my XIMR band to have greater intensity. In another word, for a moment just believe that this is XIMR. If this is XIMR, then with concentration it should increase. Yeah, with concentration this should increase, but as a matter of fact it does not. So, that is why you must separate from XIMR to XIplex like this concentration. So, this kind of photophysical studies ought to be done, which I am not telling in all cases, but we always do photophysical studies also. We also do excitation spectra. So, excitation spectra of this system will be similar, will be mirror image of absorption spectra. If that is the case, then my compound is not decomposing under radiation, because you have to heat it with some radiation, all right, monochromatic radiation to excite it. And if it decomposes, then my excitation spectra will be different from the absorption spectra. Okay. So, if that is identical similar features, then I know that my compound is photostable. So, these kind of photophysical studies must be made. Number one is taking excitation spectra of the fluorophore of this system, and number two, just see whether I can get other peaks also, okay, other peaks also. And if suppose a metal ion is here, then I do not see any XIplex, it comes, okay. Had it been XIMR, I would have seen this, because this XIMR is because of outside, they will stack, whether metal is inside or there does not matter, all right. So, it will stack, it stacks means XIMR if it gives emission. So, these two are very important, which I did not mention earlier, but as I am trying to emphasize that when you get a system, when you get a fluorescent signaling system, and it is a very interesting one, you get a new system nobody has done before, but you have done for the first time, then you have to do these photophysical studies, okay. You have to do these photophysical studies, all right. So, these 2 points must be taken note of. Another important, okay. So, now coming back to this system, we have seen that these cryptands are having poor chemoselectivity, okay. Cryptands poor selectivity, chemoselectivity, cryptand has poor chemoselectivity. Poor chemoselectivity means when I put a copper 2 ion, we see strong fluorescence. We put a nickel 2 ion, we see strong fluorescence. Iron, manganese, cobalt, you name it, we see very strong fluorescence. Then I put main group metal ions. For example, I put lead, I put cadmium, I put mercury, okay. Always I see, so this is a disadvantage. Not only those, even if I put lanthanides, okay, lanthanides are actinide. Suppose I put europium or cerium or neodymium, I will always see fluorescence, okay. So that way this is no good, poor chemoselectivity. What I want specific, but unfortunately that was not there. The importance of this work is that this was the first example of transition metal induced fluorescence enhancement. So that was a very, very important point. Now doing this work, we found we are very unhappy, okay. So we tried to make, so from tris we made mono and bis as well. You make mono This fluorophore is anthracene, remember. So I am not writing too many. Mono and bis. What is the effect? Still it shows poor chemoselectivity, these systems, okay. So this is NH. Valency must be satisfied, no matter whether you do photochemistry or photophysics or whatever study, supramolecular or not, valency must be satisfied. Okay, so we make bis or mono. Then also what happens, some more metal ions can enter because they are more accessible. If you have tris, means is kind of jumbled up, so other metals may not get into. But if you make mono or bis, they also work perfectly, transition metal induced fluorescence and all that. Then then you can increase, you can play with this kind of systems, photophysics. You can increase this from methylene to ethylene to propylene. What happens? If you do that, then the communication between fluorophore and nitrogen decreases because it is a saturated linkage. Then two things happen. PET is not very efficient, and therefore, if you increase that, PET not being very inefficient, enhancement factor is low. Okay. So that is one important point. So methylene works best because from methylene it can easily go, it can easily PET is easily achieved and very efficient. Okay. So now this part is then covered. Okay. Now while doing this, after few years, this was made. after few years, this cryptand is same as the one that I made, remember, but this is now cartoon because I do not have time to or maybe I should draw it first time, whether you are understanding anything. Let me draw it. You might also ask at this point, did you change this cryptand and see whether it is poor chemoselectivity or not? Yes, we did. We tried many cryptands, many cryptands and put these fluorophores and tried. They were all poor chemoselectivity. So, results was same, but still the importance remained. So, while after some time we tried this compound. I am drawing pyrene, this is a pyrene. Okay, pyrene is connected here. Okay, pyrene, and then we put don't ask me, for God's sake, why did you do this? Okay, don't ask me, because it was something other, something we wanted to do that. All right, and then dinitrobenzene moiety attached to this. When we do this, what happens? This particular cryptand becomes rigid cavity, okay, rigid cavity, and some spectacular thing happens. What happens is, now we get, if we put a transition metals or lanthanides or any other metal, doesn't work. It works only for cadmium. So, it is a now cadmium 2 specific, cadmium 2 plus. So, when I put a cadmium here, okay, let me write with a color code. Cadmium 2, so I put a cadmium 2 here. I see a very strong fluorescence. Okay, I see a very strong fluorescence of what? Of pyrene, not anthracene, but pyrene. Why pyrene? Which I will tell you later. That is another phenomenon. So, we wanted to do such this phenomenon, that is why we did. only cadmium 2 specific. So, we have achieved specificity. I will tell you another cryptand, another story, and where you have this. Let me draw the picture properly. I do not need that. You have I made a mistake. I really need it. Okay. I need this. I made a, yeah, that's why I made a mistake. I like to see it. NH, okay. That N was missing. Okay. Okay. So, this is a cryptand. Okay. This is a cryptand. I am not telling you how to synthesize this cryptand, but this is a cryptand. Okay. And I am drawing now one coumarin derivative fluorophore. I will take couple of minutes more, that is all. Okay. Okay. This is a coumarin derivative. Okay, coumarin derivative, carboxylate. This particular compound, let me get a couple of more minutes. You have copper here. It can take copper, 2 coppers, specifically for copper. And the distance is such that only carbonate can fix here, carbonate, CO2 minus, okay, oxygen and carbon and oxygen, okay, carbonate anion, okay, CO3 anion can fit here, it can bind. Okay, now what happens? When I have no CO3 in the medium, then copper 2 binds at this point, copper 2 binds. This carboxylate goes in and binds copper. So, when we excite the coumarin, it gives it goes to excited state, but because copper is transition metals, so no fluorescence, quench, no fluorescence. But if it can take up carbonate from air, it can take up carbonate from air, or we can give excess carbonate, then it fits perfectly here. That is why it will come, it will displace coumarin, okay. It will displace coumarin. As a result, coumarin upon excitation gives a very strong fluorescence, okay. So, I will take up from this point onwards in my next class. Thank you.